Simplilearn. Your pace, your place.
Hello and welcome to the introductory lesson of the Big Data and Hadoop Developer course offered by Simplilearn. In this lesson, you will be introduced to the Big Data and Hadoop Developer course. Let us explore the objectives of this course in the next screen. By the end of this course, you will be able to describe the fundamental concepts of Hadoop, apply programming skills in MapReduce, utilize big data analytic skills using Pig and Hive, explain the HBase data model and its components, describe how ZooKeeper and Sqoop address the challenges associated with distributed computing. In the next screen, we will focus on the course overview. This training course provides a detailed introduction to the basics of Apache Hadoop. It will also enhance your knowledge of the Hadoop ecosystem, Hadoop distributed file system, Hadoop cluster, MapReduce, Pig, Hive, HBase, ZooKeeper, Sqoop, Flume, and so on. In addition, this course will provide an overview of the installation and configuration steps for various Hadoop components. You will learn how to install and configure the environment in the Ubuntu server operating system. Finally, you will learn how to perform programming and analytics using Java and other Hadoop ecosystem components. We will continue with the course overview in the next screen. The course is aimed at professionals who aspire to perform big data analytics using Apache Hadoop. Analytics professionals, IT professionals, ETL developers, project managers, and testing novices, and experts benefit from doing the course. Other aspirants and students who want to gain a thorough understanding of the implementation of Hadoop framework can also benefit from this course. Now let us discuss the prerequisites of this course. Knowledge of any programming language is a basic course prerequisite. Participants are expected to have fundamental programming skills to understand and implement MapReduce operations using Java. A working knowledge of Java will be an added advantage for this course, though it is not mandatory. In the next screen, we will discuss how this course can add value to participants. Hadoop professionals will be equipped with Hadoop framework skills in the fast-growing big data analytics industry. They will be able to process a huge amount of data with a high level of efficiency as the industry switches over from Excel-based analytics to real-time analytics. By equipping you with thorough knowledge and the required skill set, this course helps you differentiate yourself from other big data professionals. The demand for Hadoop professionals will be high over the next decade in all leading organizations worldwide. They will be able to derive benefits from the emerging big data industry once they are equipped with the required knowledge and skills. In the next screen, we will focus on the list of lessons covered in this course. There are 13 lessons covered in this course. The table lists the lesson numbers with their corresponding names. Hello and welcome to Lesson 1 of the Big Data and Hadoop Developer course offered by Simplilearn. This lesson will provide an introduction to big data. Further, it will introduce Hadoop as a big data technology. Let us explore the objectives of this lesson in the next screen. By the end of this lesson, you will be able to identify the need for big data, explain the concept of big data, describe the basics of Hadoop, and explain its benefits. In the next screen, we will focus on the huge data explosion we usually experience every day. Over the last decade, there has been an unimaginable explosion of data in every sector. By an estimate, over 2.5 exabytes of data is generated every day, equivalent to 2.5 billion gigabytes. This huge volume of data originates from various sources. Following are some of these sources. A typical large stock exchange, such as the New York Stock Exchange, captures more than 1 terabyte of data every day. There are around 5 billion mobile phones in the world, of which 1.75 billion are estimated to be smartphones. YouTube users upload more than 48 hours of video every minute. Every second of HD video generates more than 2,000 times as many bytes as are required to store a single page of text. Large social networks like Twitter and Facebook capture more than 10 terabytes of data daily. There are more than 30 million networked sensors in the world, and each of them sends in data continuously. In the next screen, we will discuss the types of data. Data can be identified as one of three primary types. The first is structured data, which can be represented in a tabular format and stored in relational databases like MySQL, Oracle Database, DB2, and so on. The second is semi-structured data, which does not have a formal data model, though it may have some semblance of a structure. For example, XML files represent semi-structured data. The third is unstructured data, which does not have a predefined data model. Text files, web logs, and machine logs are examples of unstructured data. In the next screen, we will discuss the need for big data. By an estimate, around 90% of the world's data has been created in the last 2 years alone. Moreover, 80% of the data is unstructured or available in widely varying structures, which are difficult to analyze. Through the years of developing IT systems, we have observed that structured formats like databases have some limitations with respect to handling large quantities of data. It also has been observed that it is difficult to integrate information distributed across multiple systems. Further, most business users do not know what should be analyzed and discover requirements only during the development of IT systems. As data has grown, so have data lakes within enterprises. Potentially valuable data for varied systems like ERP or Enterprise Resource Planning and SCM or Supply Chain Management is either dormant or discarded. It is often too expensive to justify the integration of large volumes of unstructured data. Information such as natural resources has a short useful lifespan and is best used in a limited time span. Further, information is best exploited for business value if context is added to it. In the next screen, we will focus on data as the most valuable resource. Data is fast becoming like oil, which used to be considered the most valuable natural resource in terms of monetary value. In its raw form, oil has little value. Once processed and refined, it helps power the world. The same holds true for data or information. In its raw form, data has little value. Once processed and refined, it helps power the world. That is why Clive Humby commented on CNBC that data is the new oil. In the next screen, we will define big data and discuss its sources. Big data is an all-encompassing term for any collection of data sets so large and complex that it becomes difficult to process them using on-hand data management tools or traditional data processing applications. Some of the sources of big data are web logs, sensor networks, social media, Internet text and documents, Internet pages, search index data, atmospheric science, astronomy, biochemical and medical records, scientific research, military surveillance, and photography archives. In the next screen, we will focus on the three characteristics of big data. In this screen, we will discuss the characteristics of big data technology. Big data technology helps to respond to the characteristics discussed in the previous screen. It helps to cost-efficiently process the growing volumes of data. For example, as per IBM, big data technology has helped to turn the 12 terabytes of tweets created daily into improved product sentiment analysis. It has converted 350 billion annual meter readings to better predict power consumption. Big data technology also helps to respond to the increasing velocity of data. For example, it has scrutinized 5 million trade events created daily to identify potential frauds. It has helped to analyze 500 million daily call detail records in real time to predict customer churn faster. Big data technology can collectively analyze the widening variety of data. For example, it has helped to monitor hundreds of live video feeds from surveillance cameras to target points of interest for security agencies. It has also been able to exploit the 80% data growth in images, videos, and documents to improve customer satisfaction. According to Gartner, big data is high-volume, high-velocity, and high-variety information assets that demand cost-effective, innovative forms of information processing for enhanced insight and decision-making. In the next screen, we will focus on the appeal of big data technology. Following are the reasons why big data technology is popular and has been attracting attention. Big data technology helps to manage and process huge amounts of data in a cost-efficient manner. It analyzes all available data in their native forms, which can be unstructured, structured, or streaming. It captures data from fast-happening events in real time. Big data technology is able to handle failure of isolated nodes and tasks assigned to such nodes. It can turn data into actionable insights. In the next screen, we will categorize the sources of data. In this screen, we will discuss the traditional approach to develop IT systems. The following are the requirements of the traditional IT analytics approach and factors they are challenged by. The traditional IT analytics approach requires the business team to define questions before IT development. Further, the team needs to define data sources and structures beforehand. The business team is usually challenged if they have iterative and volatile requirements or if data sources keep changing. The image illustrates the traditional IT analytics approach. In a typical scenario of traditional IT systems development, the requirements are defined, followed by solution design and build. Once the solution is implemented, queries are executed. If there are new requirements or queries, the system is redesigned and rebuilt. In the next screen, we will discuss the approach taken to build big data systems. This approach requires the business team to define data sources and establish the hypothesis. Here, big data technology should enable explorative analysis. The IT team should integrate data systems and sources are required based on new business questions and the hypothesis. The image illustrates how IT systems are built with the help of big data technology. At the onset, the initial data sources are identified. The IT team creates a platform for creative exploration of available data and content. The business team determines the questions to ask and tests their hypothesis. Any new question leads to the addition of data sources and integration without the need to redesign and rebuild the platform. In the next screen, we will discuss the capabilities of big data technology. Big data technology helps you to understand and navigate big data sources, manage and store a huge volume of a variety of data, process data in reasonable time, ingest data at a high speed, analyze unstructured data, and bear faults and exceptions. In the next screen, we will discuss the various use cases of big data. Big data technology appeals to various sectors and is used for a variety of use cases. As per Cloudera, the technology has found uses in industries such as automotive, communications, consumer packaged goods, financial services, education and research, high technology and industrial manufacturing, life sciences, media and entertainment, online services and social media, healthcare, oil and gas, retail, travel and transportation, utilities, law enforcement, and defense. In the next screen, we will discuss how to handle the limitations of big data. There are two key challenges that need to be addressed by big data technology. These are handling the system uptime and downtime and combining data accumulated from all systems. To overcome the first challenge, big data technology uses commodity hardware for data storage and analysis. Further, it helps to maintain a copy of the same data across clusters. To overcome the second challenge, big data technology analyzes data across different machines and subsequently merges the data. In the next screen, we will introduce the concept of Hadoop, which helps to overcome these challenges. Hadoop helps to leverage the opportunities provided by big data and overcome the challenges it poses. Hadoop is an open-source Java-based programming framework that supports the processing of large data sets in a distributed computing environment. Hadoop runs a number of applications on distributed systems with thousands of nodes involving petabytes of data. It has a distributed file system called Hadoop Distributed File System, or HDFS, which enables fast data transfer among the nodes. Further, it leverages a distributed computation framework called MapReduce. In the next screen, we will discuss the origin and history of Hadoop. Hadoop originated from the Nutch open source project on search engines and works over distributed network nodes. In 2003 and 2004, Google released two papers that provided insight into their success. The Google File System, or GFS, and MapReduce simplified data processing on large clusters. The papers told the world how Google performed large-scale data processing. In July 2005, Nutch used GFS to perform MapReduce operations. In February 2006, Nutch started a Lucene subproject, which led to the era of Hadoop. In April 2007, Yahoo started using Hadoop on a 1,000-node cluster. In January 2008, Apache took over Hadoop and made it a top-level project. In July 2008, a 4,000-node cluster with Hadoop was tested by Apache. The performance of that cluster was surprisingly the fastest when compared with other technologies implemented that year. In May 2009, a test revealed that Hadoop successfully sorted a petabyte of data in 17 hours. Hadoop reached version 1.0 in December 2011. It is completely open source and written in Java. In the next screen, we will discuss how organizations are using Hadoop. Yahoo was the first company to design and use Hadoop as a core part of their system operations. Now Hadoop is a core part of systems at Internet companies like Facebook, LinkedIn, Twitter, and many enterprise organizations such as JP Morgan, Chevron, and so on. The table displays the names of organizations, the cluster specifications, and the way they have made use of Hadoop. Let us summarize the topics covered in this lesson. Big data is a term applied to data sets that cannot be captured, managed, and processed within a tolerable elapse and specified time frame by commonly used software tools. Big data relies on volume, velocity, and variety with respect to processing. Data can be divided into three types: unstructured data, semi-structured data, and structured data. Big data technology understands and navigates big data sources, analyzes unstructured data, and ingests data at a high speed. Hadoop is a free Java-based programming framework that supports the processing of large data sets in a distributed computing environment. Hello, and welcome to Lesson 2 of the Big Data and Hadoop Developer course offered by Simplilearn. This lesson will help you get started with Hadoop. Let us explore the objectives of this lesson in the next screen. By the end of this lesson, you will be able to list the steps to install VMPlayer, list the steps to create a VM in VMPlayer, explain how to use Oracle VirtualBox to open a VM, explain how to start an existing Hadoop VM. In the next screen, we will discuss VMPlayer. VMPlayer is a free software package offered by VMware Incorporated. It is used to create and manage virtual machines. During a hands-on session on Hadoop and its ecosystem components, you will be applying all theories in the VM created within the VMPlayer. The VMPlayer can be downloaded for personal use from the URL shown on screen. In the next screen, we will discuss the hardware requirements for installing VMPlayer. The basic hardware requirements for working on VMPlayer are as follows. At least 1 GHz of processor which can support Intel VT or virtualization technology, 1 GB RAM, and 150 MB of hard disk space to install the application. However, it is recommended to have 2 GHz of processor and 2 GB RAM for optimum performance. In the next screen, we will learn to install VMPlayer. Perform the steps shown on screen to install VMPlayer. Initialize the installation process. In the installation wizard, click Next to continue. Select the destination folder and click Next. Upgrade the product by selecting Check for Product Updates on Startup. Click Next, Continue, and Finish for the subsequent screens. Double-click on the desktop icon for VMware Player. Accept the license agreement and click Next. In the subsequent screens, we will see how to perform the steps for the installation of VMware Player. In the next screen, we will initialize the installation process. Double-click the VMware Player executable file for initializing the installation process. The window shown on screen will be displayed. Click Save File to continue. In the next screen, we will continue to discuss the steps for installing VMware Player. The installation wizard gets activated and displays the welcome screen for installation of VMware Player. Click Next to continue the installation process. In the next screen, we will continue to discuss the steps for installing VMware Player. The destination folder window appears, giving users an option to either install the software in the default location or in a specific location. Accept the default location and click Next to continue the installation process. In the next screen, we will continue to discuss the steps for installing VMware Player. The Check for Product Updates on Startup section will be displayed. The checkbox is selected by default. Click Next to continue the installation process. In the next screen, we will continue to discuss the steps for installing VMware Player. The wizard provides options to create VMware shortcuts. Check the boxes and click Next to continue the installation process. In the next screen, we will continue to discuss the steps for installing VMware Player. The installation wizard states that the installation process is yet to begin. Click Continue. In the next screen, we will continue to discuss the steps for installing VMware Player. The installation wizard displays the Setup Wizard Complete section. Click Finish to complete the installation process. In the next screen, we will continue to discuss the steps for installing VMware Player. Double-click on the desktop icon for VMware Player, accept the license agreement, and click Next. In the next screen, we will continue to discuss the steps for installing VMware Player. The window shown on screen is displayed. VMware Player is installed successfully. In the next screen, we will list the steps to create a VM in VMware Player. Perform the steps shown on screen to install VMware Player. Click Create a new virtual machine. Select I will install the operating system later and click Next. Select the appropriate guest operating system and version. Choose VM name and location name and click Next. Specify the disk capacity by providing the disk size. Select Store Virtual Disk as a single file and click the Next button. Once finalized, click Finish to create VM. In the subsequent screens, we will perform the steps to create a VM. Install VMware Player in your system. The window shown on the screen will be displayed. Click Create a new virtual machine. In the next screen, we will continue to discuss the steps to create a VM. Select I will install the operating system later and click Next. In the next screen, we will continue to discuss the steps to create a VM. Select the appropriate guest operating system and version that need to be installed in this virtual machine and click Next. In the next screen, we will continue to discuss the steps to create a VM. Choose the appropriate virtual machine name and location to store the VM files and click Next. In the next screen, we will continue to discuss the steps to create a VM. Provide the maximum disk size in gigabytes. Select Store Virtual Disk as a single file and click Next. In the next screen, we will continue to discuss the steps to create a VM. A screen that shows the summary of the VM settings previously chosen is displayed. Click Finish. In the next screen, we will learn to open a VM using VMPlayer. The window shown on the screen is displayed, which means the VM is created successfully in the VMPlayer. Click Open a virtual machine to open an existing virtual machine. In the next screen, we will continue to discuss how to open a VM using VMPlayer. Open the Hadoop pseudo-server VM by selecting the VMX file provided by Simplilearn and click Open. In the next screen, we will understand how to open a VM using an Oracle VirtualBox. Alternatively, the Oracle VirtualBox can be used to open virtual machines. Generally, Apple Macintosh users use this free VMPlayer, since VMware Fusion Player is usually available for trial or limited usage. Download the latest version of VirtualBox compatible with your machine and firewall settings from the URL shown on screen. In the subsequent screens, we will perform the steps to open a VM using VirtualBox. Open Oracle VM VirtualBox Manager. Click Machine tab and select New to create a new virtual machine. The Create Virtual Machine window is displayed. Enter the name and target operating system and click Next. In the next screen, we will continue to discuss how to open a VM using Oracle VirtualBox. Allocate the desired memory size to the virtual machine and click Next. In the next screen, we will continue to discuss how to open a VM using Oracle VirtualBox. Select Use an existing virtual hard drive file and click Create. In the next screen, we will continue to discuss how to open a VM using Oracle VirtualBox. The selected VM file is displayed. In the next screen, we will discuss a business scenario to understand the use of VMPlayer. Olivia is the EVP of IT Operations with Neutro Worldwide Incorporated. Olivia plans to work from home. To do so, she has to access her system remotely from her home computer. Her home computer has a different operating system than the one in her office. She has just installed VMPlayer on her home computer and wants to start working. The demo in the subsequent screen will illustrate how to work on virtual machine VM. Though the following demonstration shows how to work on the VM for Windows platform, these steps can be applied to start a VMPlayer across all platforms. In the next screen, we will view a demo to start the Hadoop VM provided by Simplilearn. Let us do a quick recap of the steps performed. Let us summarize the topics covered in this lesson. The VMPlayer executable file is used to install the VMPlayer. A VM can be created in the VMware in 5 steps. The Oracle VirtualBox can be used to open virtual machines. Hadoop VM provided by Simplilearn is a pre-configured VM with Hadoop installed in Ubuntu Server 12.04 OS. Hello, and welcome to Lesson 3 of the Big Data and Hadoop Developer course offered by Simplilearn. This lesson provides detailed information of the Hadoop architecture. Let us explore the objectives of this lesson in the next screen. By the end of this lesson, you will be able to describe the use of Hadoop in commodity hardware, explain the various configurations and services of Hadoop, differentiate between regular file system and Hadoop distributed file system HDFS, explain HDFS architecture. In the next screen, we will discuss some key terms used in Hadoop architecture. An understanding of some key terms is essential while discussing Hadoop architecture. The word commodity hardware refers to normal PCs which can successfully be used to make a cluster. The word cluster refers to multiple systems interconnected in the same network to logically work for one process in distributed mode. And nodes are the commodity servers which are interconnected through a network device. In the next screen, we will discuss the use of commodity hardware in a Hadoop cluster. Hadoop is a framework which is often used in commodity hardware. It supports the concept of distributed architecture. The diagram represents the cluster of nodes connected and installed with Hadoop. The maximum number of nodes that can reside in a single rack is around 30 to 40. However, it is not an exact count. You can have more number of nodes with an adequate network speed. Normally, the uplink from rack to node is 3 to 4 gigabytes per second. The uplink from rack to rack internally is 1 gigabyte per second. In the next screen, we will study Hadoop configuration. There are 5 core Hadoop services: name node, data node, job tracker, task tracker, and secondary name node. Generally, in fully distributed mode, the name node, secondary name node, and job tracker are termed as master services, whereas the data node and task tracker are termed as slave services. In the next screen, we will study the core components of Hadoop. There are 2 major components of Apache Hadoop. They are Hadoop Distributed File System, abbreviated as HDFS, and Hadoop MapReduce. HDFS is used to manage the storage aspects of big data, whereas MapReduce is responsible for processing jobs in a distributed environment. In the next screen, we will discuss HDFS. HDFS is used for storing and retrieving unstructured data. Some of the key features of Hadoop HDFS are as follows. HDFS provides a high throughput access to data blocks. When unstructured data is uploaded on HDFS, it is converted into data blocks of fixed size. The data is chunked into blocks so that it is compatible with the commodity hardware's storage. HDFS provides a limited interface for managing the file system. It ensures that one can perform a scale up or scale down of resources in the Hadoop cluster. HDFS creates multiple replicas of each data block and stores them in multiple systems throughout the cluster to enable reliable and rapid data access. In the next screen, we will discuss MapReduce. The MapReduce component of Hadoop is responsible for processing jobs in distributed mode. Some of the key features of the Hadoop MapReduce component are as follows. It performs distributed data processing using the MapReduce programming paradigm. It allows you to possess a user-defined map phase, which is a parallel share-nothing processing of input. Also, it aggregates of the output of the map phase, which is a user-defined reduce phase after a map process. In the next screen, we will differentiate a regular file system from HDFS. A comparison between a regular file system and HDFS is shown on screen. In a regular file system, each block of data is small, usually about 51 bytes. However, in HDFS, each block is of a very large size. It is 64 megabytes by default. A regular file system provides access to large data, but this feature of the file system may suffer from disk I/O problems, mainly due to multiple seek operations. HDFS can read huge data sequentially after a single seek, which makes it unique since all these operations are performed in distributed mode. In the next screen, we will list the characteristics of HDFS. There are certain basic characteristics of HDFS that make it popular. HDFS has high fault tolerance. An HDFS instance may consist of thousands of server machines, each storing a part of the file system's data. Since we have a huge number of components and each component has a non-trivial probability of failure, there is always some component that is non-functional. Detection of faults and quick automatic recovery is a core architectural goal of HDFS. HDFS provides high throughput. HDFS is designed to store and scan millions of rows of data and count or add some subsets of the data. This may take a few minutes or much longer depending on the complexity involved. Traditionally, HDFS has been designed to support high throughput on large data sets in batch-style jobs. HDFS is suitable for applications with streaming access to file system data. These are not general-purpose applications that typically run on general-purpose file systems. HDFS is designed more for batch processing than interactive use by users. The emphasis is on high throughput of data access rather than low latency of data access. Also, HDFS is designed in a way such that it can be built on commodity hardware and heterogeneous platforms. In the next screen, we will list the key features of HDFS. The key features of HDFS are as follows. HDFS creates multiple replicas of each data block and distributes them on computers throughout a cluster to enable reliable and rapid access of data. HDFS is the storage system for both the input and output of MapReduce jobs. The file system can be accessed by using the HDFS protocol to perform I/O operation on the file which is stored in HDFS. Block storage metadata controls the physical location of a block and its replication within the cluster. Each block is replicated to a small number of physically separate machines, for example, 3 machines. However, the count can be modified by the administrator. In the next screen, we will discuss HDFS Architecture view. A typical HDFS setup is shown on this screen. This setup shows the 3 essential services of Hadoop: name node, data node, and secondary name node services. The name node and the secondary name node services constitute the master service, whereas the data node service falls under the slave service. The master service is responsible for accepting a job from clients and ensuring that the data required for the operation will be loaded and segregated into chunks of data blocks. HDFS exposes a file system namespace and allows user data to be stored in files. A file is split into 1 or more blocks, stored and replicated in data nodes. The data blocks are then distributed to the data node systems within the cluster. This ensures that replicas of the data are maintained. In the next screen, we will understand the HDFS operation principle. HDFS components include different servers like the name node server, the data node server, and the secondary name node server. The name node server is the core component of an HDFS cluster. There can be just one name node server in an entire cluster. It is responsible for maintaining the file system namespace. The name node server is responsible for managing the files and directories in the file system tree. Information of the data and the metadata is stored in the namespace image and the edit log. The name node is aware of the data node status. That is, it knows the data node in which certain data is stored. The name node server is a critical single point of failure. If it fails, the entire cluster goes down. However, the name node server can be partially restored by using a secondary name node server. Data node is a multiple instance server. There can be n number of data node servers depending on the type of networking and storage system that a setup has. The data node servers are responsible for storing and maintaining the data blocks, which are provisioned by the name node server on the basis of the type of job submitted by the client. The data node server is responsible for storing and retrieving the blocks when referred by clients or the name node. The data node servers read, write requests, and perform block creation, deletion, and replication upon instruction from the name node. There can be only one secondary name node server in a cluster. It is responsible for maintaining a backup of the name node server. But you cannot treat the secondary name node server as a disaster recovery server. It will only partially restore the name node server in case of failure. The secondary name node server maintains the edit log and namespace image information which is synced with the name node server. Sometimes the namespace images from the name node server lag behind, due to which we cannot totally rely on the secondary name node server for the recovery process. In the next screen, we will discuss HDFS. HDFS is a master-slave architecture which consists of a single name node and a data node. HDFS is also responsible for maintaining the file system namespace and allowing user data to be stored in files. The file is split during the map phase into multiple blocks, and these blocks are stored in a set of data nodes, ensuring that the replication factor is maintained. The name node helps to execute file system namespace operations like opening, closing, and renaming of files and directories which are present in HDFS. It also determines the linking of blocks to data nodes. Data nodes are responsible for performing read and write requests in HDFS based on the client's request. Data nodes also perform block creation, deletion, and replication on instruction from the name node. The name node and data node are pieces of software designed to run on commodity machines. In the next screen, we will discuss the file system namespace of HDFS. HDFS exposes a file system namespace and allows user data to be stored in files. HDFS has a hierarchical file system with directories and files. It supports operations like create, remove, move, rename, etc. The name node maintains the file system and records any change to meta information. In the next screen, we will understand name node operation. The name node manages the file system namespace, allowing clients to work with files and directory subtrees. HDFS supports a traditional hierarchical file organization. A user or an application can create directories and store files inside these directories. The file system namespace hierarchy is similar to most other existing file systems. One can create and remove files, move a file from one directory to another, or rename a file. The name node maintains the file system namespace. Any change to the file system namespace or its properties is recorded by the name node. The name node maintains two persistent files, a transaction log called edit log and a namespace image called FS image. The edit log records every change that occurs in the file system metadata. For example, creating a new file. The edit log is stored in the name node's local file system. The entire file system namespace, including mapping of blocks to files and file system properties, is stored in the FS image. This is also stored in the name node's local file system. However, metadata loads into its memory what blocks of data reside on which data nodes at startup, when new data nodes join a cluster, and periodically thereafter. When the name node starts up, it gets the edit log and FS image from its local file system, updates FS image with edit log information, and then stores a copy of the FS image on the file system as a checkpoint. The metadata size is limited to the RAM available on the name node. Since a large number of small files would require more metadata than a small number of large files, the in-memory metadata management issue explains why HDFS favors the latter over the former. If a name node runs out of RAM, it will crash and applications won't be able to use HDFS until the name node is online again. In the next screen, we will study data block split. Each file is split into one or more blocks stored and replicated in data nodes. Data nodes manage names and locations of file blocks, which are 64 megabytes each by default. For large files, it is better to increase the block size to 128 megabytes. Doing so decreases pressure on the name node's memory. On the contrary, this potentially decreases the amount of parallelism that can be achieved as the number of blocks per file decreases. Since each map task operates on one block, if there are tasks lesser than nodes in the cluster, jobs will run slower than they could. The larger the individual files involved, or the more files involved in the average MapReduce job, the lesser an issue this is. In the next screen, we will understand the benefits of the data block approach. Some of the benefits of the data block approach include simplified replication, fault tolerance and reliability, and shielding of users from storage subsystem details. In the next screen, we will understand the data block replication architecture. In HDFS, unstructured data is represented in the form of data blocks. The default size of the blocks is 64 megabytes. However, block size can be reset by the user or the administrator. HDFS performs block replication on multiple data nodes so that if any error exists on one data node server, the job tracker service, which is present in the name node server, will resubmit the job to another data node server. Block replication refers to the creation of replicas of a block in multiple data nodes. Usually, the data is split in the form of parts like Part 0, Part 1, etc., as shown in the image. The image also represents the parts that are stored in multiple data nodes. In the next screen, we will discuss the replication method. Each file is split into a sequence of blocks. All blocks in the file except the last are of the same size. Blocks are replicated for fault tolerance. Block replication factor is usually configured at the cluster level, but can also be configured at the file level. The name node receives a heartbeat and a block report from each data node in the cluster. Block report contains all the blocks on a data node. An application can also specify the number of replicas of the file needed, that is, the replication factor of the file. This information is stored in the name node. In the next screen, we will discuss a suggested data replication topology. In terms of replication, one of the suggested replication topologies could be having the first replica placed on the same node as the client. The second replica is placed on a rack different from the first rack. The third replica is placed on the same rack as the second rack, but on a different node. In the next screen, we will understand a pictorial representation of replication topology. On this chart, we see a Hadoop cluster with 3 racks represented by the dark blue pillars. Each rack contains multiple nodes represented by rectangular boxes within each rack. For example, on the far left, you'll see a box labeled R1N1, which represents node 1 on rack 1. For simplicity, each rack shown here has 8 nodes. At the top, you see the name node shown in yellow. Let's follow the path of one particular data block. block B1, shown in purple on this chart. B1 is first written to node 4 on rack 1. A copy is then written on a different rack, rack 2, in this case. In fact, it's written to node 5 on rack 2. The third and final copy of the block is written to the same rack as the second copy, rack 2, but a different node, which is node 1, in this example. In the next screen, we will discuss various ways to access HDFS. HDFS provides various access mechanisms. We can use a Java API for applications. There is also a Python and C language wrapper for non-Java applications. We can also utilize Web GUI through an HTTP browser. An FS shell is available for executing commands on HDFS. In the next screen, we will discuss a business scenario related to HDFS. Olivia Tyler, the EVP of IT Operations with Nutro Worldwide Incorporated, has decided to use HDFS for storing big data. She will be using an HDFS shell to store the data in the Hadoop file system and execute various commands on it. The demo in the subsequent screen illustrate how to perform basic command line operations on HDFS. Let us do a quick recap of the steps performed. Let us summarize the topics covered in this lesson. Hadoop works on 3 configurations, namely standalone mode, pseudo-distributed mode, and fully distributed mode. The 2 core components of Apache Hadoop are HDFS and MapReduce. The HDFS layer contains name node, secondary name node, and data node. HDFS can be used to handle big data sets with its inherent features of fault tolerance, high throughput, and streaming data access. In the next lesson, we will focus on Hadoop deployment.